We've seen the supernova legacy survey results move towards the Planck values. Wendy, you've had a week. How are you doing with H0? So anyway, so instead, what we're going to do is each of the panelists is going to have 5 or 6 minutes with a few transparencies, economical transparencies, Dick, and we'll cycle through the panelists and then invite questions from the floor. Okay? So, John.
Can you hear me? Yeah. I have to look over here. Okay, so his question to me, and Dick's, and George's question to me was really, John, you really should address the SPT plus WMAP data versus Planck. But before I even get there, because I know, actually, I would think for a panel summary, that's the last thing you want to hear. But based on the number of questions I've gotten this week, at least some of you want to hear. But I want to start with really the top, which is that Planck is really magnificent. It's an incredible achievement. You guys have done an amazing job. Congratulations to everyone. I know personally how much work it is. I didn't expect to see so many papers in this first release. So amazing. It's great. We're all scientists, though, so we like to look at the details. Certainly in the Planck papers, I looked at our details, and this last week was my opportunity to look at yours a little bit. So I want to address this. How do they compare? Especially since George and Dick have pulled us aside to say they actually phrase this title differently sometimes. So I'll get there. One thing I also want to point out is that these data sets, WMAP, ACT, SPT, and Planck, are an amazing agreement. They're really quite precise. And beyond that, if you forget for a second the adding external data sets, they actually agree. They agree very well. There's a couple parameters I'll talk about where they maybe don't, and I don't quite understand why. But they agree even on extensions to the model for the most part, which are quite controversial. It's when you add external data sets, which give more or less tension with these, that you start to push around. And as George pointed out in his first day, if you add external data sets and there, for whatever reason there's some tension, new physics will emerge, but perhaps it's not new physics, perhaps you're something wrong with the data. Well, we don't know that till you do the exercise. So one of them I want to talk about is higher omega matter. That has to do with this difference here. Another theme that's been throughout the conference has been clusters. I work in clusters, so I thought I would show some of that. And then what's next for CMB? Lyman's talk, I think, did a great job. Planck is terrific, it really is. But it's just going to keep getting better from Planck, but also from the field for the next few years, especially in polarization. So let me go to the next slide. So this is the point. It's actually in the appendix of the cosmology paper. This is a cutoff here to show where SPT data is published. So it's not going down to the lower multiples. This is the Planck model based on Planck data and SPT, and here are the residuals. So let's start on the right. You can't even see our points. They're hidden under the line. It's beautiful. It's great. And as you move down, there is no Planck data at that high L. You see the Planck data a little high. We could talk about that. But this basically looks very good. There's this funny kind of pattern, but it looks very good. The big point in this appendix is, what happened to you, John, down here? And really, there's a few points high, a bunch right on the line, a couple low, but the mean is a little high. It's not statistically significant. That's where we overlap with MAP, though, so there's concern that when we combine our data with WMAP, that could skew things. And one thing that was asked to me, you must have seen dust. That must be dust. It must be dust cirrus. Well, the FDR models, I mean FDS models, and now the WMAP dust models, we can go look in our fields, and the answer is no. There's not enough dust. It's about 0.5% maybe. All the other foregrounds are taken care of. So that's not it. Maybe it's sample variance. Well, these error bars are sample variance error bars. The actual statistical errors are much smaller. Those are the sample variance error bars. So I'll show you our comparison to Planck in this field. Right? So in other words, take Planck data, take the 143 gigahertz map, look in our field, treat it the same way, mask out the point sources, mask them a little bigger because Planck's beam is much bigger, and see what we get. But first I want to point out that when we combine SPT and WMAP, the change in cosmology from Planck, here's those two cosmologies, it's all at low L. That's what's driving it. In fact, what's really driving omega matter, I'll talk about it more, is that the fact that this first peak is a lot higher in WMAP. Anyway, let's see, what else do I have here? Can't read my own view graphs. So let me go on. So this is taking, as I showed, as I explained, I mean, the WMAP, sorry, the Planck data in our field, 143 gigahertz, just saving the same modes on the sky that we measure, same masking, and comparing them. So it's Planck crossed into SPT, divided by SPT into itself. So it's the ratio. This is our calibration error. We're calibrated only about 2.6% in power. And this is the Planck beam uncertainty. We see no slope, we see no excess. It all looks very good. So I hope that at least gets people thinking again. And then when you recalibrate our data within the calibration area, you get this number we've all seen before, a couple percent difference where Planck is lower. But that's within the SPT calibration area. Going further, now I'm not going to talk about this. This is also a figure from the appendix, but Lyman showed, compared to WMAP9 data, the Planck data, SPT, and all the data sets, and it appears there is some change. This is with WMAP residuals and compared with WMAP scaled down. There is some change when you go to higher L, you start to drop. So there's some, not just calibration, as Lyman showed, but some actual L dependence. So anyway, when you do that, you know, the peaks are different. You get a little more matter density. That's one thing that seems to happen. Not saying who's got it right, but it's different. This is another thing that Planck in their papers, when they solve for the lensing, how much lensing is in the data, and you can get this parameter called A lens, essentially turn off its effect on your parameters. So this is just with the A lensing parameter on or off. This is omega matter, and you can see that first off, they're high, we're low, WMAP's in the middle. If you add the 4-point, that is the lensing reconstruction, drops down a little bit. And if you just turn off this smoothing in the peaks, their peaks are smoother than ours, you drop down again. We, if you do the same thing, go up, and we overlap. So there's something funny that we don't understand. That's something to look into. And these peaks, how sharp are they or not? And this is just the same thing on cold dark matter, but also in H0. You come in. So the most serious disagreement that I know between the two data sets is omega matter, and actually seems to be tied to this difference in WMAP and this smoothing of the peaks, which I don't understand what would do that. Onward. So enough of that. Clusters. So we heard a lot about clusters through the meeting, and the amazing thing to me, you know, yes, clusters are very messy. We always hear lots of caveats. But if you look at clusters, they give consistent sigma-8 results from many different techniques and many different experiments. I mean, we're talking about SE counts, the bispectrum, the power spectrum and the SE, X-ray counts, weak lensing from Planck, SPT, Chandra, and XM. They're all more or less in agreement. And they're kind of down in this regime here. Whoops. This up here, this is sigma-8 versus omega matter. This is the power spectrum, you know, from the CMB projecting what sigma-8 should be. This is Planck. This is WMAP, and this is SPT with WMAP, right? So we're pushing down. If you change omega matter, things change. So omega matter actually is important. So what could cause these, what could bring these all together? Clusters are messy. Maybe we don't understand their mass. Maybe we're off by almost a factor of 2. Maybe we're missing 2/3 of all the massive clusters. Well, I crossed that one out. I don't think we're doing that. Maybe, as I said, omega matter is too high. Most likely, it's some combination of all these three. But one thing I just want to say is if you ignore clusters, you do so at your own peril. They have been bellwethers of problems in the past, it's important to keep, pay attention to that. So anyway, we have to figure this out. There's a big campaign by lots of groups now to understand the mass calibration of clusters. We'll learn a lot more about these power spectrum results over the next year, and we'll see what happens here. Once we do, then we can really decide or figure out if we need new physics. Because another way to bring these all into agreement is to give a little mass to the neutrinos. So we're not ready to say the neutrinos have mass, but that's coming. And I want to just tap into Lyman's talk, is that we're going to learn a lot more about neutrino mass and a lot of things from the CMB lensing polarization measurements.
Thank you. Thank you, John.